In this video, we're going to be taking a look at problem 4 from Practice Exam 3-1 in the Fall 2021 semester in Chem 12-11. And let's start by taking a look at the question statement. So we've got the ground state electron configuration for a given atom with 6 valence electrons has 2 unpaired electrons in the 3p orbitals. Enter the chemical symbol for the element that this electron configuration describes. So essentially what we're doing here is unpacking this first sentence to generate an electron configuration for a neutral atom and then identifying that neutral atom based on its number of valence electrons and position on the periodic table. So at the heart of this problem is electron configuration. Now, in getting started with this problem, 6 valence electrons, we really need to unpack that phrase. 6 valence electrons does not mean 6 electrons total. We're not necessarily looking at carbon, which actually only has 4 valence electrons, or oxygen with 6 valence electrons. The element could be oxygen, but the second half of the sentence actually tells us that the element is not oxygen. We've got 2 unpaired electrons in the 3p orbitals. This immediately tells me that the valence shell is n equals 3. The valence shell is n equals 3. And so we're probably looking here at an element in the third row of the periodic table. And in order to proceed, what I would do is draw an orbital energy diagram of the n equals 3 shell, the n equals 3 valence shell, and start filling electrons until I can achieve this 2 unpaired electrons situation with a total of 6 valence electrons. So let's do that, and let's start then by laying down the subshells in the n equals 3 shell. We're going to have a 3s level and a 3p level. There will be a 3d level, but with only 2 unpaired electrons in the 3p subshell, we haven't filled the 3p subshell entirely, and so the 3d subshell will be completely unfilled, completely empty. So we only need to worry about these 2 subshells within the n equals 3 shell. And now let's proceed through a kind of trial and error approach where we just start filling electrons into these orbitals and see where we end up once we've filled in 6, because after all, this is the valence shell, right? This is the valence shell as we've written it right here. So let's lay down 6 electrons in accordance with 2 key ideas. The Aufbau principle, this is starting from the lowest energy orbital and moving upward, and Hund's rule, which tells us when we've got degenerate orbitals, we're going to fill each orbital with 1 electron before pairing electrons up to avoid electron-electron repulsion and all that good stuff. So starting at the bottom, 2 electrons in the 3s orbital with opposite spins. I'm going to follow Hund's rule in the 3p subshell. And now if we pause right here, I've got 2 unpaired electrons. I've got 2 unpaired electrons in 3p orbitals in this electron configuration. And this would point me to an element, the second element of the p block in the third row of the periodic table. N equals 3 is the valence shell, so we're in the third period. And this gets me to silicon. Is silicon the correct answer? Be careful. 6 valence electrons, and so far we've only laid down 4. In order to get to 6, we need to add 2 more electrons. And to do that, we're going to add a third electron in that last unfilled 3p orbital, and then 1 more electron paired with the first in the 3p subshell in that first orbital we filled. And now let's check that we've satisfied all of the conditions of this first sentence. 6 valence electrons, I do have 6 valence electrons, and I do have 2 unpaired electrons highlighted in purple right here. So I have satisfied the conditions of that first sentence. And where does that leave me on the periodic table? Well, let's take a look. N equals 3, shell, so I'm in the third row of the periodic table. This is the valence shell, N equals 3. And I'm in the p block because I'm filling up the 3p subshell. I've got 4 electrons in the 3p subshell, 1, 2, 3, 4. This puts me at sulfur. So the element in question is sulfur, and the chemical symbol is, of course, S. And there you have it. So this problem was all about deducing an electron configuration for a neutral atom from a textual description of the electron configuration. A great conceptual problem for electron configurations of heavy atoms.